Here we go with our last example of linear systems of equations, and again, this would be assignment number 28. Two variables, both variables to the first power, line, two variables, both to the first power, line. We've established either they cross at a point, that'll be our answer, or maybe they're parallel. They're practicing social distancing. Anyway, of the choices we have for solving this particular system, I hope you would say, you know what, that top equation says y equals, and therefore we can substitute this expression that's equal to y in the other equation. And so we'll put this in for y in that bottom equation. And when you put one thing in place of another, that's called substitution. So that bottom equation will therefore transform into negative 8x plus 2 times quantity in the parentheses equals negative 18. All right? The principle behind that is the transitivity property, which is exemplified from this movie clip. Sorry to bother you with this. This is from the movie Lincoln years ago. And so let's enjoy a clip very quickly.
Newton's first common notion is this: things which are equal to the same thing are equal to each other. That's relevant, but mathematical reason it's true because it works. As the number, always relevant. In his book, Newton says this is self-evident. You see what it is, even in that 2,000-year-old book of mechanical law, it is a self-evident truth that things which are equal to the same thing are equal to each other.
Things that are equal to the same thing are equal to each other. All right? Well, that's what's happening here. See, we're putting the expression that's equal to y in that top equation in for y in the bottom equation. Things that are equal to the same thing are equal to each other. All right, anyway, that was worth it, wasn't it? Now, that's one variable, so we go ahead and solve it. And we have negative 8x plus 8x minus 18 equals negative 18. Combine like terms. Those get rid of each other. We're left with negative 18 equals negative 18. There's no variables left. We've seen this before. Now, there's no variables left to solve for. But, unlike the previous example, aren't those numbers indeed equal? Okay? So the visual that goes with this would be that instead of there being no solution, wouldn't this mean basically that if you were to graph these two lines, they are actually indeed the same line? That's the interpretation that follows from something like that. And so we would say, well, how many ordered pairs do these lines have in common if they're in fact the same line? And the answer would be, there's an infinite number of points that they have in common. There's a lot of ways to report the answer to this. My preferred of the many that are available would be the phrase, infinitely many solutions. That tells the person looking at the work that you have acknowledged that these two graphs are indeed the same graph, and therefore they have an infinite number of points in common. That would be my preferred way of answering it. Others have other ways of saying it. But anyway, and I want to share with you, as we leave this, one of my favorites. I don't know if you'll be able to see it very well, but one time a person on their paper got 0 equals 0, which would be just like that, infinitely many solutions. And this person wrote infinitely many. Infinitely. 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 Am I supposed to count that wrong? I probably am. I'm not going to count you down for spelling, but look at your notes and spell it right. What's infinitely many mean? A bunch of babies? I don't know. So anyway, I thought that was kind of humorous. That wraps up assignment 28. All right? I hope you had infinite fun with that.